So now let's talk about a proof. And what I want to do is I want to prove this. We have all the tools that we need. It's actually not that complicated. There's some small technical details we'll need to handle, but we'll do that. So what I want to show is we'll show that capital F prime is equal to little f. And actually, we're going to show, I just want to emphasize what we're really going to show. We're going to show that this is equal to 0. Capital F prime of z minus little f of z is 0, and therefore they're equal. To do that, what we're going to do is we're going to have to work with the limit definition of the derivative, because that's really all that we have. I mean, we don't know what the function little f is. We can't say anything about its antiderivative a priori. So we just have to work with the limit definition. We don't have a choice. So what we're going to do is we're really going to look at, we're going to consider the limit definition of, so the limit definition of the derivative involves finding the limit of the difference quotients. So we're going to look at the difference quotients minus little f. So we're going to consider capital F of z plus h minus capital F of z all over h minus little f of z. Okay, and then what we're going to do is we're eventually going to just mess around with that quantity to the extent where we can take the limit and show that the limit of this quantity goes to 0. Okay, so that's going to be our goal. That's going to be our game. Now, notice that capital F of z plus h minus capital F of z, well, capital F of z plus h is going to be the integral of f over the line integral of gamma sub z plus h. So what this means is that we're starting with the fixed point z naught, and this is going to be the line integral from z naught to that point z plus h. And then we're going to subtract from that the line integral from z naught to z. Okay, so that's what, just by definition, that's what these are. But just think about what's happening here if you have a silly primitive drawing here. Here you have some point z. Here you have some point z plus h. And what we're thinking about is the line integral from, say, z naught to z, in the line integral from z naught to z plus h. And what we really want to think about is going from z plus h to z. So we're really going to look at that piece. And if you think about it, this is going to be the integral from z naught to z plus h minus the integral from z naught to z. If you just think about vector subtraction, that should be a natural enough idea for you there. Even though these aren't quite vectors, they're paths, but same idea. And so that's what this is going to work out to. And it turns out that this is going to be the integral over f of, let me actually just highlight it here, this green path. Okay, so this is going to be the integral over f over some path gamma, where gamma is any nice path from z plus h to z. So where gamma is any piecewise smooth continuous, so piecewise smooth continuous path from z plus h to z. Okay, and so that's what we're left with. So this is that quantity there. So that's the numerator of this first fraction that we're going to look at. So now I want you to notice that if I'm thinking about f of z, well, we can think of, let's think about our integrals as integrals of w, because z is taken. So I don't want to use the integral with respect to z if I have an f of z that's already been specified. So we just have to be a little bit careful about that. But now let's look at what actually is the quotient that we're looking at. We're looking at f of z plus h minus f of z, those are capital F's, all over h, minus little f of z. That's really, if you think about it, 1 over h times this quantity that we were just looking at, times the integral over gamma of f of w dw, again, where gamma is any continuous piecewise smooth path from z plus h to z. One other thing I just want to point out, if you integrate the constant 1 over gamma, what you're going to get is you're going to get, by the fundamental theorem of calculus that we talked about before, the antiderivative of 1 is just z. So you're going to get the endpoints subtracted from each other. So you're going to get z plus h minus z, which is just h. So it turns out that the integral of 1, so this is important enough, I just want to emphasize, the integral of 1 over gamma is going to turn out to be h. So what we can do is we can factor out an h in f of z here. And then that is going to be useful because this is going to be 1 over h times the integral over gamma of f of w dw minus the integral of f of z dw, because f of z is just a constant with respect to w, so we could bring it in and out of the integral with no problem. Okay, and so really we can write this as a single integral. This is the integral of 1 over h times the integral over gamma f of w minus f of z. Integral is with respect to w. Okay, so we did, just to emphasize, we did two things there, just to be clear. I multiplied and divided by h, and then we factored it out. And that's where this h came from. And then this h we wrote as the integral of 1 dw, but f of z is a constant, so you can move that in and out of the integral. So that's basically what we did there. Now, this is the quantity that we're going to have to look at, and we're going to take the limit as h goes to 0. So what we're going to do, if we just think about the limit definition, so the epsilon delta definition of a limit now, is we have to play around with that just slightly. So by some of the properties that we know, if we take, I want to make sure that this is completely crystal clear. What I'm going to do now is I'm going to take the modulus of both sides. So the modulus of capital F of z plus h minus f of z over h minus little f of z is going to be equal to the modulus of 1 over h times this integral, gamma f of w minus f of z dw. And then what we can do is we can apply a few things. So first of all, we can take the modulus of h outside the integral with no problem. So nothing really interesting there. And then we can move the absolute value, the modulus rather, inside the integral at the cost of making that a less than or equal to. And moreover, we know that we can bound that by the length of gamma times the maximum value of the integrand. So this is going to be the maximum value of w in gamma of f of w minus f of z. So whatever that largest value is, that's what we're going to have. And this is going to be what we need to deal with now. So just off to the side, I want you to remember two things. I want you to remember that gamma is a path from z plus h to z. And I also want you to remember that if we're talking about here remember h is a complex number. So there's just a few things to keep track of. Here, h is a complex number. And so just a few things to point out. If the modulus of h is small enough, then it turns out that gamma will be in G, right? Because we're talking about a path from z plus h to z, and we're thinking of h is going to 0. So certainly wherever z is, since we're talking about an open connected region, we can choose h enough to be as close to z as we want, and therefore that path will be completely in G. I hope that makes sense the way that I said that. But if the modulus of h is small enough, gamma is in G and everything there is fine then. We don't have to worry about leaving G, but it is important that G is open and connected. So we're using that hypothesis. We have to have the hypothesis that f is continuous. And because f is continuous, we can say a few things about what this quantity is going to be. So for example, we know that since f is continuous, we know that for all epsilon, there exists a delta. So for all epsilon, there exists a delta. So that if the modulus of z minus w is less than delta, then the modulus of f of z minus f of w is less than epsilon. And actually, I want to do that. It makes no difference because these are the same terms, but let's just make it consistent. So let's do the modulus of w minus z, and that implies that the modulus of f of w minus f of z is less than whatever our epsilon is. I'm actually going to choose epsilon over 2 for reasons that I'll explain in a second. Okay, so I'm going to choose epsilon over 2 there. I also want you just to think about the following fact, that the length of gamma is always going to be less than or equal to twice the length of, twice the modulus of h. H is going to be the distance between, so we can choose gamma so that this is true, but h is going to be the distance between z and z plus h, and you can always choose gamma so that its length is less than twice the distance between the 2 points. And really, I mean, there's no, we don't really need this condition, but this condition is helpful. So the length of gamma is less than or equal to twice the modulus of h. And then with that, if we call this star, what this shows is that the modulus of capital F of z plus h minus capital F of z all over h minus little f of z, if we take the modulus, that's, I'm just going to rewrite what we have. That's less than or equal to this stuff. So that's less than or equal to 1 over the modulus of h times the length of gamma times the maximum value of f of w minus f of z, where the maximum is taken over all values w in gamma. And based on what we said, the length of gamma is less than or equal to, so the modulus of h will leave alone, the length of gamma is less than or equal to twice the modulus of h. And because of continuity, f of w minus f of z, if we stay within delta units of z, then this quantity is going to be less than epsilon over 2. So that's going to be less than or equal to epsilon over 2. So I could actually say, if I want, that this is strictly less than, because these two things are equal. The length of gamma is less than or equal to 2 times the modulus of h, and the maximum value here is strictly less than epsilon over 2. So I can write strictly less than there. And this, of course, is just epsilon. And what this shows is that this value is going to be less than, this value is going to be less than epsilon for all epsilon, and therefore it must be 0 as h goes to 0. So by definition of a limit, so by the epsilon delta definition of a limit, this tells you that the limit as h goes to 0 of this quantity, capital F of z plus h minus capital F of z all over h minus little f of z, is 0. And what that tells you is that the limit of this quantity without the modulus is 0, because we know that this was, I think, one of the exercises in the beginning of chapter 1, but we know that if we have a quantity, so first of all, we can bring the modulus out, and we know that the modulus of z is going to be 0 if and only if z is 0, right? And so this tells you that the inside, the limit is going to end up being 0, and therefore we're done. So this tells you that capital F prime of z is equal to little f of z. Okay, and so that's the proof. This has been largely editorialized from the way that the book does it. The book does it pretty similarly, but that's the idea. Okay, so there's the proof of the fundamental theorem of calculus for complex integral.